All right, so we took a look at how to solve these integration constants. C1, we already did C2, C3 and C4. And now the final thing to do is to plug those values back into the original functions here that we have. So we'll plug C1 back in to find the concentration through the Pyrex, or how that concentration changes through the Pyrex as we move along in Y. And we'll plug C3 and C4 back into the second profile. And what we'll have is a piecewise function that describes the concentration of helium as it's diffusing through these materials. Recall the whole goal here was to verify that through this control volume analysis, we ended up with the same result that we got with a very simple resistance network. And so we're trying to verify that that value that we got on the exam does match what we can get through these functions here. So let's say plugging these back in, actually, this yields in the Pyrex, we have the concentration from 0 to the interface equals to the original concentration plus Y over Yi times the diffusion of A through the silicon dioxide over the diffusion coefficient of the helium through the Pyrex. So we have the ratio of the diffusion coefficients times the original concentration. This is over quantity 1 minus H over the interface thickness, Yi, minus that ratio of diffusion coefficients. So as you turn the paper sideways, kind of a big function here, the way we've written it. You might be able to play around with algebra and make that a little smaller. But in the silicon dioxide, we will have, let's see, this function is going to be the concentration from the interface as we move around in Y up to the thickness of H equals Y minus H over Yi, the interface thickness, times Ca naught, all over the same denominator that we have in the concentration of the Pyrex here. 1 minus H over Yi minus Ta through silicon, the diffusion of helium through silicon over the diffusion coefficient of helium through Pyrex. All right, so those are the two functions we ended up with. And I told you it might be a little easier to find the flux with a resistance network. And I think that I have proven my point. But we need to do one final thing here before we finish this solution, and that is to check and make sure that these functions satisfy the original boundary conditions that we specified. So in this box here, we outlined what we expect in the system, right? The bounds we applied. And we need to verify that these two functions will satisfy these boundary conditions and make sure that we solve these integration constants correctly. So that is the next step. All right. So the first boundary condition that we applied was the concentration at Y equals 0 has to be the initial concentration. So let's see, that has to do with the concentration through the Pyrex. And what we need to do is plug in y equals 0 to this function and make sure that we end up with the original concentration. And it looks like we don't need to do too much work here. If we plug in a 0 for y, this term goes away and we get that the concentration of A equals the original concentration. So good, we're satisfied this boundary condition. We have at the interface, we have to match concentration. That's going to be a little bit of work. Let's put a pin in that for 1 second. I think we can evaluate this integration constant, or this boundary condition, pretty readily. So the concentration of A at y equals H, that has to do with the concentration in the silicon dioxide. And so if we plug in an H for y, we had better come up with a 0 concentration. And if we plug in an H for y, we get H minus H is 0. We get a 0 multiplying this entire function, and sure enough, we do get the concentration at y equals H is 0.